Hi folks, welcome back to Advanced Math, Unit 12 on Vectors, Part E, pages 1 and 2, the Yorkshire Canary Enclosure, revisited. So the first part of this, first page of the section, there isn't anything for you to do. It's just a review of the things we've done up to this point. So the relationship between the equation for a plane and the components of a vector that would be perpendicular to the plane works the same way for a line. And so it's just a little brief rundown here about how you work between those two, the plane equation and the components of the vector. And then moving on, we go down and take a look at the once again looking at the picture of the Yorkshire Canary enclosure, which was introduced way back in the beginning of this whole exercise. So nothing to do here. Just move on. Now, there's a piece of the description about the canary cage that's important to us, and that's a description of exactly how that post works that holds up the roof. And that's captured here in this passage. The post rises from the center of the floor to a height of 10 feet above the floor. The post is not perpendicular to the floor. The top of the post is directly over a point that is 2 feet north and 3 feet west of the center of the floor. So another way of visualizing this is if you took a piece of string with a weight on it and held it up at the top of the post and gently lowered the string, or the weight on the strings until the weight touched the floor, you would find when that string and the weight touched the floor that that point would be 2 feet north and 3 feet west of the place where the post touches the floor. So we're going to use this information to describe a vector that is used to model that post. And so we have here a vector shown, and this is actually done in one of the homework assignments. We have an x component. Now the x component, let's say that is the east-west direction. So the east to the east would be positive x, and to the west would be negative x. And for the y component of that vector, we'd say that that was north and south. That's south, trust me. So north is plus and south is negative. And then the z-axis, well, that would have to be up and down. So that up represents positive and down represents negative. So if you look at the three components of this vector, the first component, that x component, is the east-west component. The second component is the north-south component. And the third is the up and down. And you'll notice right away that that third component, the up-down component or z component, is 10. And that 10 is coming from this piece of the description. The post rises from the floor to a height of 10 feet above the floor. So that's the z-axis direction. The 2, which is the north-south component, comes from this piece of the description, and the negative 3 comes from that piece, 3 feet west of the center of the floor. So that's how we get all three components of that vector. And now to review what Zach the carpenter needs to figure out. He needs to figure out the height of the roof above the floor at the corners of the roof, A, B, C, and D, the lengths of the four sides of the roof, which, because the corners are A, B, C, and D, we'll call the sides of the roof A, B, B, C, C, D, and D, A. And then, in order to construct the roof, Zach needs to know the angles formed by those edges. So measure the angles, measure of angles at each corner of the roof. So even though the floor is rectangular, we suspect, maybe your intuition tells you this, that the roof is not, because the roof is canted at an angle above the floor. So before we begin this analysis, we need to come up with make some decisions about some things. One of them is where everything is needed to be described using this x, y, and z coordinate system. And in order to figure out what the x, y, and z of everything is in this roof and the bird cage, we need to have decided where the origin of the axis system is. And actually, the results of this analysis don't aren't determined in any way by where your origin is. You can choose the origin anywhere, and the number should work out the same. But there are possibly, some origins that would be more useful than others. Now, we did say that the floor of this cage is a thickness of 1 foot, and but you know what? I'd prefer to ignore that. So I actually would like to say that the z equals 0, the reference for the 0 z value should be on top of the foundation, the level of the floor. So if you're standing on the floor of the bird cage, the place where your foot is, that z equals 0. So I would say, and you could do this differently, but my preference is to say that the origin is the place where the post meets the floor. And so once you've done that, the next question is, well, what are the coordinates of the base of the post? Well, if we said the origin is the base of the post, where the post meets the floor, then the coordinates of the base, let me change colors, are 0, 0, 0. And that's not a vector, that's just a position of coordinates, the point in space. Now, if the post vector P is that vector we had higher up in the page, -3, 2, 10, and um, that vector, if we position that vector so that the beginning of the vector is at the origin, where would the end of the vector be? Well, if you put a vector and start it at the origin of the axis system, the end point of the vector is going to be at a point whose coordinates are exactly the same as the components of the vector itself. This is why this is so nice. So now I can say the post top is -3, 2, 10. Now again, this is a little bit of a blurring of the lines between what is a vector and what is a point. If you have vectors that originate at the origin, the ends of those vectors will be at points whose, whose components are the same as the components of the vector that got you there. So in that situation, the coordinates of points and the components of vectors to those points are the same numerically. They're kind of interchangeable concepts. Okay, next up, we're going to get into some cool math, arithmetic really.